Good morning, everyone. So welcome to the 13th Electron Devices and Solid State Circuits online seminar. So this is also part of the Hong Kong UST Academy of Continuing Education Open Seminar Series. Today, we are very honored to have Professor Zhongrui Wang here. He is currently an assistant professor with the Department of Electrical and Electronic Engineering at the University of Hong Kong. Dr. Wang received both bachelor degree with first honor and PhD degree from Nanyang Technological University in 2009 and 2014, respectively. He did his postdoc research at the University of Massachusetts Amherst. His research interest lies in emerging memory-based neuromorphic computing and machine learning, as well as modeling Memrister materials using density functional theory. He has authored more than 50 technical papers, including first authored articles on Nature Review Materials, Nature Materials, Nature Electronics, Nature Machine Intelligence, and Nature Communications, which have received more than 4,000 citations. His results have been reported more than 40 times by mainstream scientific and popular media resources. Without further ado, let's welcome him to give the seminar. Professor Wang, you may go ahead.
Thanks, Professor Shao, for the introduction. It's my very great pleasure and honor to have this opportunity to share my research on bio-inspired computing with memristors. So here is the goal of our research. So one of the ultimate pursuit of electrical and computer engineers is to devise a machine that can be human-like. The reason of having such a goal is pretty simple. Such kind of robots could free human beings from our daily works. But things could also go opposite. For example, like human beings could become the batteries of the robots, like what is depicted in the movie Matrix. But no matter whether the robots will be our slaves or human will become the slaves of robots, there is one thing that is becoming more and more clear. That is, the goal to make an intelligent machine is more achievable than any time else. That's why we're trying to develop human-like intelligence. For example, computers can now drive cars. The automobile maker Tesla is about to launch. It has set its goal to launch fully self-driving cars in a couple of months. But don't worry if you already have a Tesla. This is because you may still be able to upgrade your car with a full self-driving computer installed, like the one shown in this video. Despite cars, our cell phones are becoming more and more smarter. They can partially understand what we are talking about and do whatever we ask them to do. To some extent, the latest development of generative language models like GPT-3 is almost able to talk in a human-like manner, despite it may not really understand what's the meaning beneath. Moreover, computers have also defeated human beings in the game of Go. In fact, Google DeepMind has expanded its triumph in a lot of other games, starting from Atari games in 2015 to even StarCraft 2 in last year. Some of those games were believed that human would long dominate. And all these changes actually took place in very recent years. So we may have a very natural question. What enabled these kind of changes? The answer is the hardware, or the computers that act like our brain. For example, the general-purpose graphic processing units, like the one shown here, an NVIDIA V100 graphic card, which was one of the flagship graphic cards by NVIDIA. It was one of the most powerful one, but now it has been. It was the most powerful one when this slide was prepared, but now it has been succeeded by its predecessor, the A100, with 80 gigabyte high bandwidth memory and an astonishing bandwidth. In addition, big companies like Google, Qualcomm, and Intel have their own chips. For example, Google has built its famous tensor processing units, and now it's developing the fourth generation of tensor processing units. Qualcomm has developed the so-called Cloud AI 100 that is based on ARM architecture. While for Intel, the story is a bit tragic. Uh, Intel bought a company named Nirvana, but eventually it bought another one, which is Habana, based in Israel. So now which develops the so-called Gaudi and Goya processors for training and inference of neural networks. In addition, there is another class of chips that draw a higher degree of inspiration from the brain, or the neuromorphic chips. In fact, the most biggest difference between these two categories of chips is that the chips on the right-hand side can't be bought online, like from Amazon or from eBay. They 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 are confined to the research lab at this moment. And the members of this category include some of the very famous names, such as the Loki processors of Intel and the True North processors of IBM. I would like to introduce a little bit more on what's the difference behind like these two categories of chips. For neuromorphic chips, those on the left-hand side are neuromorphic chips. They are designed to replicate the functionalities of our brain. For example, in the brain or a neuromorphic chip, they consist of neurons and synapses. Each of the neurons integrates the incoming spikes of the upstream neurons. Uh, the neuron will integrate, and once the stimulation exceeds a threshold, the neuron will produce its own spike, or the so-called action potential, uh, which is the red which is the red spike depicted here, that will propagate along the axon to reach the downstream neurons. And the interface between two neurons is this kind of junction, or the so-called uh, synapses. Then they are not only simple junctions, but they are able to modulate the signal transmission strengths across two neurons by very complicated chemical cascade reactions. These synapses actually are responsible for our memory and and the the reason that uh, we are intelligent. Uh, a unique feature of such synapses is that they change the transmission strength of signals across the synapse by their own. That which means actually by their plasticity. That means the transmission strength of signal across the synapse is determined by the historical signals that has passed across a synapse. On the other hand, these are so-called machine learning chips. It's it's kind of abstracted from a neuromorphic system. That is, we simplify the neurons to nodes in a computational graph, and the synapses as the arrows in this graph, where a synapse represents multiplication. Actually, it's the same way to modulate the signal transmission between two neurons, while the neurons sums up the incoming stimulation followed by a nonlinear activation function. And usually the strength of the or the like weights of synapses is determined by mathematical optimization methods to lower down a global cost function. But we may have a question. No matter the machine learning chips or neuromorphic chips, are they really approaching the performance of our brain? The answer is probably not. And or in another word, how many chips can parallel the hardware configuration of our brain? The answer will be very staggering. For example, we may need 10 millions of chips just to parallel the number of synapses in the brain, because the digital version of synapses and neurons, they are truly expensive. Let's use the latest Intel Loki chip as an example. It spans more than 16,000 transistors just to simulate a single neuron and the 1,000 synapses associated with the neuron. In addition, these chips spend more than 1,000 times energy to perform a single operation compared to our brain. This is mostly because the processing units and memory units of these chips are physically separated. A lot of energy is spent on the memory access, particularly the access to the main memory or DRAM via the data bus on the usually the data buses refers to those on our motherboards. Such kind of access to DRAM is very energy inefficient, and uh, and it's also subject to and it also incurs a lot of time latency. And in fact, for machine learning systems, most of the energy so far is spent on the access to registers, caches, and DRAM. So a natural question is that how can we address the mentioned challenges? Can we resolve those? One of the most natural tendencies that can we resolve these challenges by keeping on optimizing our digital computers? And in fact, so far in the last 20 years, the advancement of our AI chips is mainly driven by two thrusts. The first is the scaling of the transistors. Now we have entered the era of 5 nanometer technology nodes. And in fact, both TSMC and Samsung has announced that they will be having 3 nanometer nodes in risk production in probably late this year. And so what's next? Can we really make 2 nanometer transistors or 1 nanometer transistors or 2D materials transistors or CNT carbon nanotube transistors to can we like really sustain our pace of transistor scaling? So this is actually a very challenging question to all physicists. Or perhaps we may end up our scaling. This is which has been lasted in the last 50 years. This is because in case if we make transistors even smaller, we are about to the node size of a transistor will be almost the same as the length of a silicon unit cell. That's unbelievable. And in addition, making transistors smaller and smaller is actually making them less and less inefficient so far. That means the transistors made at extremely small nodes may not be that cheap compared to those made at large technology nodes. Therefore, this is also another concern on whether the transistor scaling can be retained at its normal pace. The other thrust comes from the microarchitectural level and the instruction set architectural level. That is, instead of making a chip that is like very universal or that is talented in all kinds of tasks, can we make a chip that is more specific but more efficient in a specific task, or the so-called ASIC, application-specific ICs? Um, in fact, most of the machine learning at this moment is no longer performed by our central processing units, which is a very universal processor. It's good at all kinds of tasks, but unfortunately, it's not that efficient because it's not fully optimized for a specific task. We're mostly working on graphic processing units. It's relatively efficient, more efficient than central processing units, but less efficient than application-specific units, but it's more flexible. That means we are still be able to implement different kinds of neural networks on our GPUs. So it's kind of a trade-off between efficiency and the flexibility. And it's anticipated we will be moving more and more towards ASICs in future because the tasks, the like machine learning tasks, are becoming more and more specific. But in fact, no matter, uh, uh, in fact, even so far, even the ASICs, they are still facing the challenges that the memory and processing units are physically separated, which means they are not they are not be able to resolve this challenge or the energy per operation. They are not able they are unable to make this characteristic or the energy per operation parallel to that of our brain. So it seems that all our traditional approaches to advance the digital electronics are unable to address the requirement that is to make a machine that is truly as intelligent as a human being. So it seems that some fundamental changes to the computing paradigms must be implemented. For example, a fundamental change of our building blocks of the computing systems. Um, One of the most promising candidates of such building blocks is Memrister. It's a mathematical concept coined by, mm, conceived by Professor Liang Chua back in 1970s. It's actually a dynamic system or a Markov chain. In 2008, people from HP Lab have proved theoretically that a resistive switch, actually a tunable resistor, its equivalent, it meets the general definition of a memristor, as revealed by its name, a mem and resist, or essentially a resistor with memory. Its conductance depends on the history of applied electrical signals. So far, memristors have been realized on various physical processes. For example, in a redox memristor or redox resistive switch, an electric field could ionize silver or copper atoms. They will be driven by the electric field to migrate towards the other electrode and being reduced there, thus forming a metallic filament shorting the two electrodes, making the device of lower conductance. On the other hand, reverse electric field or at elevated temperature may be able to rupture the conducting filament and recover its resistance. In a phase change memristor, in a phase change memristor, a long but low amplitude electric pulse will heat up the memristor above its crystallization temperature, so the chalcogenide glass will gradually relax to its crystalline position. Those atoms will gradually relax to their uh, like to the crystalline configuration. On the other hand, a very high amplitude voltage pulse, but with very short duration, will melt the chalcogenide glass and quench it very quickly, thus leading to the amorphous uh, chalcogenide glass that is very resistive. Therefore, switch the resistance of the phase change memristor between the two states. In magnetoresistive memristor, this is one of the most promising memristor, and it's now entering the massive production as an embedded memory of the processors by Intel, by Samsung, and GlobalFoundries. And Professor Shao is a leading figure in this field. This kind of memristor operates on the tunnel magnetoresistance that is determined by whether the magnetization of the two ferromagnets are parallel or not. Therefore, it features very limited randomness during switching. And in addition, the magnetization of one of the ferromagnet can be flipped over by either spin torque transfer, voltage controlled magnetic anisotropy, as well as spin orbital coupling. And the last method, spin orbital coupling, actually features potentially the least amount of programming energy as well as best reliability. So magnetoresistive memristor is one of the most promising future candidates among all memristors. In addition, in a ferroelectric memristor, the tunnel resistance is determined by the polarization direction of ferroelectric domains. And the polarization direction of such ferroelectric domains could be flipped by applying a sufficient large electric field or the coercive electric field, so that the tunnel resistance can switch between different states. These unique switching mechanisms of memristors actually provide memristor with some dynamic processes that can be utilized for computation purpose. As to be discussed in the following slides, a single nanoscale memristors, electrochemical memristors, is able to simulate the dynamic behaviors of synapses and neurons. This is because synapses and neurons, they are also dynamic systems operating on electrochemical reactions, while the redox memristor itself is also a dynamic system but operating on solid state electrochemistry. On the other hand, memristors, because they are dynamic systems, so they combine both memory and processing capability. The tunable conductance of a memristor could be used to store information, and in this way, they are also named resistive random access memory. And on the other hand, being a tunable resistor, memristors, particularly especially when they are in an array formation, can be used to perform vector matrix multiplications using Ohm's law for multiplication and Kirchhoff's law for summation. As a result, a memristor array can the matrix is stored as the conductance of this memristor array, while the vector is represented by the amplitude of the input voltages, and the output vector are the currents flowing through these columns. And since this kind of vector matrix multiplication is highly parallel, this is because the currents appearing in different columns will be generated at the same time. In addition, this kind of computing is also very energy efficient because the elements of the matrix, they are stored by memristors, and they are also used to process the input to process the input vector by the same memristors. Therefore, there is no data shuttling between the memory and processing units. This makes this kind of computing uh, so-called in-memory computing that gets rid of the inefficient uh, and very delayed data shuttling between the memory and the processors. Another important feature of memristor is that they are made of very simple structures, very capacitor-like structures. A three-mask process consisting of two metal electrodes and a dielectric that is embedded by two metal electrodes, which is of a very low fabrication cost. And more importantly, they are very easy to be stacked in a three-dimensional way. Such 3D stacking could significantly increase the density of the devices. For example, my early lab has demonstrated 8-layer stacking of redox memristors. In addition, the simple capacitor-like structures also makes memristors scaling straightforward. We can simply shrink the size of a device by making the electrodes narrower and narrower. And my early group has demonstrated memristors of 2 by 2 nanometer junction size, just a few hundred of atoms. And in addition, the distance between two memristors is just a few nanometer, probably around 6 nanometer. This leads to a device density that is around 4.5 tera devices per square inch. What does this density means? It's almost comparable to the density of a 64-layer state-of-the-art 3D NAND flash memory. So with these unique features, I would like to show you two examples on how memristors can benefit both neuromorphic computing and machine learning. In the first example, a memristor with novel ionic dynamics is developed to simulate certain synaptic and neuron behavior, which will be used to build hardware spiking neural networks. As mentioned, to solve the issue that a large number of transistors are needed to simulate a single synapse or neuron, one of the solutions is to develop a memristor that shares similar dynamic behaviors with synapses and neurons at the molecular level. For example, we built a planar memristor with gold electrodes and silver nanoparticles scattered between the two electrodes. When the electric field is applied, the silver nanoparticle will be stretched into a filament, as you see here, which shorts the two electrodes. More interestingly, when the voltage is removed, the silver filament will spontaneously retract into a ball shape, very much like a liquid droplet, due to surface diffusion of silver atoms. This is observed for the first time under a TEM. This memristor is thus able to resemble the evolution of presynaptic calcium ions. When stimulation comes, the ion channels are switched on, so the calcium ions will flow into the presynaptic compartment and to trigger associated chemical reactions. In the meanwhile, calcium ions are constantly removed by ion pumps and exchangers. This similarity allows us to build an artificial synapse made of two memristors in series. The upper memristor is a silver memristor, which operates on the formation and the rupture of silver filaments in solid electrolyte. Roughly speaking, the number of silver atoms within this dielectric or the switching layer is somehow correlated to the number of calcium ions within the presynaptic compartment in a chemical synapse. The more the calcium ions, the more the neuron transmitters or these blue bubbles are released. The lower memristor is a tandem oxide memristor, which operates on the electric field induced migration of oxygen vacancies or the vacancies of oxygen atoms. Uh, the, these oxygen vacancies are very like the AMPA receptors of a postsynaptic compartment. In other words, the more the oxygen vacancies, the more the AMPA receptors, and the better the signal transmission across the two synapses. These artificial synapses exhibits both short-term and long-term synaptic plasticity, which is essential for learning in spiking neural networks. For example, it shows paired pulse facilitation when where the conductance of the silver memristors increases with the incoming spikes. In case the frequency of the incoming spike is reduced, the conductance of the memristors drops rather than increases. In addition, if a paired pulse, one presynaptic and one postsynaptic, are applied to the combined device, the silver memristor will be activated by the first pulse, and its conductance will start to decay. If the second pulse, if the postsynaptic pulse comes early enough, it will have the chance to program the tandem oxide memristor. Therefore, the conductance change of the tandem oxide memristor depends on the relative timing between the two spikes. This naturally implements one of the most important learning rules of the spiking neural networks, the spiking timing-dependent plasticity. In addition to synapses, memristors could also be used to simulate the leaky and integrate fire behavior of neurons. In this case, a silver memristor is paired with a capacitor, which plays the role of the plasma membrane. The incoming spikes will charge up the silver memristor, and once the charges exceeds a threshold, the silver memristors will be switched on because of the voltage uh, exceeds its threshold switching like upper limit. So silver the silver um, will be silver atoms will be ionized to form the filament as revealed by the color of the memristor. And after that, the silver memristor will spontaneously relax. So after that, actually the charges stored on the capacitor will be drained across the silver memristor once it's switched on. So after that, the silver memristor will relax back to its off state due to the spontaneous rupture of the conductive filament. That is because of the uh, surface diffusion of silver atoms as I mentioned in the last slide. This makes it ready to fire the next action potential, as which is shown here. The memristor synapses and neurons could be interconnected to form a neural network. This is very much like how the synapses and neurons are connected in a like how they are grouped in our brain. So we have built a proof of the concept neuromorphic chip with memristors. On this chip, there are 8 by 8 tandem hafnium oxide memristors. As these are the TEM image of a single device. Each memristor is also paired with a transistor for to isolate the device from the rest for programming and reading. And these tandem hafnium oxide memristors will work as synapses. And for each column, there are 8 such kind of synapses. They interface with a silver-based diffusive memristor neurons. These These are the TEM image of a device that is working as a neuron. So therefore the entire network is made of Memristor synapses and Memristor neurons. This chip implements a spiking neural network um, with both Memristor synapses and neurons for the first time. The input that will apply to this neural network are 4x4 patterns that such as letters, simple letters like UMAS, and with random background noise. So at each time, a quarter of the input image, a quarter of the input pattern, they will be first converted to voltages to bias the Memristor synapses. Because the Memristor synapses, they are pre-programmed to different conductance. So the neuron capacitors are charged at different rates. Those Memristor neurons that are charged fast enough will be able to fire. This is very much like how how the real neurons work. The real neurons which receive sufficient large of stimulation will be able to produce their own action potentials. And the output of the first layer, or actually a fixed convolutional layer, will be converted to voltage inputs of the second layer. The synapses of the second layer will update themselves automatically, like how the biological synapses evolve with plasticity. This is because when a neuron of the second layer fires, the original voltage drop across the synapse, the original voltage drop across the neuron will be shared by all the synapses that is interfaced with this neuron. And this extra voltage, which is very critical, will be able to program some of the memristors in case if they receive a sufficient large input. Therefore, the memristors will, uh, these memristors um, will be able to evolve in a way that is not controlled by any other external signals. And this actually physically implements a self-organization map without any digital logic control signals to compute like how much weight each synapse should be updated. In addition, reservoir computing or liquid state machine is a special type of spiking neural network inspired by our brain. The core of this network is a reservoir. It's a dynamic system consisting a large number of a large collection of spiking nodes or spiking neurons. They feature for random, sparse, and recurrent connections. The reservoir actually maps a low-dimensional input to the high-dimensional state space of these nodes, and which is usually much more linearly separable, and therefore the reservoir is followed by a simple and single readout map. That is the only layer needs to be trained or needs to learn the weights of its parameters. So reservoir computing essentially trades the training cost with hardware cost. However, Memrister actually provides a compact and low-cost solution to build the spiking neurons. For example, we can use our silver memristors to build very compact and low-cost spiking neurons rather than those which cost thousands of transistors in a digital circuit. In addition, the um, the tandem oxide or the non-volatile memristors can such kind of memristors can be used to construct the readout map. Therefore, the memristor provides a very low-cost solution to build both the spiking neurons of the reservoir and synapses of the readout map. This actually solves the fundamental issue of the reservoir computing. That is a that is expensive hardware cost. So, inspired by this, our group has built a proof of concept reservoir computing system. It consists of a reservoir made of silver-based Memrister synapses. Each silver Memrister is coupled with uh, a transimpedance amplifier and ADC to read out its current or read out the states of the reservoirs. These spiking neurons are paired with a tandem oxide Memristor array, which will work as a readout map or something like, or these uh, purple arrows. This kind of network can be used to classify MNIST handwritten digits. The handwritten digits is first preprocessed. These handwritten digits are first preprocessed in a digital computer. So each of these digits is first sliced, is first like truncated and sliced into sliced into 5 columns, and these 5 columns will be joined sequentially to form 110 by 4. Uh, Actually, they will be converted to waveforms to stimulate the silver silver memristor neurons, and the silver memristor neurons will be uh, their conductance actually will this 110 silver diffusion memristor neurons um, um, their states are represented here. These states uh, or these high dimensional states will serve as the input of this readout map, which is trained using a standard machine learning method or the stochastic regression to minimize the cause function. And this network quickly learns how to classify the handwritten digits. The experimental accuracy actually tightly follows the software accuracy, indicating robust learning of the memristors. Such memristor-based reservoir computing system is particularly good for real-time learning. This is because of its very small training cost, and it's particularly suitable for edge computing devices where the system size, and training complexity are usually the constraints. The neuromorphic applications rely on the dynamic behaviors of memristors. In addition to that, memristors can be used as a tunable resistors to compute vector matrix multiplications to accelerate machine learning. This is because vector matrix multiplication is one of the most critical operation and most frequently used operation of machine learning. So in the second example, I will show you how these memristors actually accelerate three most important applications, three most important topologies that are usually the integral of a neural network. These are the dense layers, the convolution layers, and the recurrent layers. For each layer, there will be an example. For instance, the first the dense layer will come up with reinforcement learning, convolution layer will come up with an example for pattern recognition, and recurrent layer will come up with an example for small video classification. So in a dense layer, this is a schematic of a dense layer. It's a computational graph. So every output neuron actually connects to all of the input neurons via this purple weight. So what it did is that the input neuron times the value of the input neuron times the associated weight of a synapse will lead to the value that is received by the output neuron. this can actually be translated to a Memrister array, where the synapses are represented by tandem hafnium oxide memristors. Uh, Actually, this crossbar illustrates a single memristor. Each of the memristor is actually in series connection with the transistor beneath. So the input neuron, or effectively, they are now represented by digital to analog converters. They will provide the voltages to bias the rows of the memristor array. And the output currents, like across each column, will be sensed by a transimpedance amplifier followed by an analog to digital converter. Therefore, the weighted summation represented here will be effectively performed by the Ohm's law, that governs the currents flowing through individual memristor, and the Kirchhoff's law that sums up the current. So how is the performance of this memristor-based vector matrix multiplier compared to a state-of-the-art machine learning accelerator? So here is a simple estimation. A single memristor illustrated in previous slide consists of 128 by 64 memristors. The average conductance of a memristor is around 10 kiloohm, and it's operated by a maximum voltage of 0.2 volt. Each voltage pulse may last around just 100 nanoseconds. This actually translates to an energy efficiency of 5 tera operations per second per watt for 6-bit operations, because our memristors has been experimentally proved to be able to encode 6 bits. And this is actually already twice of the energy efficiency of the first generation of Google Tensor Processing Unit that features an energy efficiency of 2.3 tera operations per second per watt. And in addition, what will happen if we can increase the resistance of each memristor to 100 kiloohm? This is a very feasible target. And reducing the voltage to 0.1 volt, reducing the voltage applied to each rows to 0.1 volt, and reduce the pulse width from 100 nanosecond down to 10 nanosecond. This will lead into an unbelievable 2 peta operations per second per watt, which will be 1,000 times of that of the first generation of Google Tensor Processing Unit. So because of this unique advantage, we built a neural network consists of 3 cascaded dense layers that are made of 3 memristor arrays. This dense neural network is used to play a simple game, that is to balance a pole on a moving cart. At each time moment, the neural network or the output neurons can tell this environment whether to give the cart a left or right push. And at the same moment, the position and the velocity, the angular position of the cart and the angular velocity of this cart will serve as the inputs to this neural network. The neural network also learns a reward signal that tells whether this cart is still upright or not. So based on this black box model, the neural network will try to figure out a strategy through trials to balance the pole as long as possible. So what we did is to employ deep Q reinforcement learning to train this neural network. So the digital computer actually will first makes a forward pass that is based on the current uh, like position, velocity, angular position, and angular velocity of the neural network that will perform a forward pass of this neural network. So based on that, the digital computer um, will then evaluate the loss function using the Bellman equation and backpropagate the error derivatives using the real memory's weight. So the errors are backpropagated. Then the digital computer will plan will plan for the weight updates with our MS prop optimizer. The weights are physically programmed and they are physically implemented by tuning the conductance of the memristors. And after that, the memristor will perform another forward pass with the updated conductance, with the updated weight to decide whether to give the card a left or right push based on the last observation or the experience. So these three layers are actually physically implemented on three memristor arrays. These color maps shows the real-time, shows the experimental evolution of the memristors along the time. So actually, in the first series, in the first 30 games, the pole actually revealed by the angle of this is the angle of the pole. You will find out the pole quickly falls. This is because the neural network has not figured out a proper strategy to balance the pole. But after that, so since the 30 game, since after the first 30 games, the memristors have gradually constructed the correlation of the input and the output based on this reinforcement learning strategy. So the pole can be kept upright as you see here, that is revealed by the angle of the pole, for much longer time in the second half of the game. So another problem from Memrister's dense network is to drive a car out of a steep valley. The car, this is a very similar game. The neural network can give the car either a left or right push or nothing at each time step. And there is a reward signal tells whether the car has reached this flag position or not. So the network is similarly implemented on a on three memristor arrays. And these are the corresponding conductance of the memristor during the course of the learning. The memristor actually spend 800 steps, so which means in the first game, the memristor has pushed the car 800 times before the car can actually reach this flag position. However, after that, the network has mastered the trick from the success of the first game. That is to swing the car back and forth to build up the momentum to so that the car can hit the flag. Another interesting finding is that the memristors actually show no degradation even after 10,000 times, 10,000 times of programming. So actually, at each time step, the memristor array will be programmed once. So after 10,000 times of programming, there's no degradation at all for the memristor arrays. This is in contrast with the lifespan of flash memories that is usually that can at most be programmed to around 100,000 times. Um, this actually makes memristors very suitable for real-time learning that has a strict requirements of the lifespan of the memory devices. Apart from dense layers, convolutional layers are widely used in computer vision and different from a dense layer. Each output neuron connects to part of the input neurons via a bundle of synapses or a so-called kernel that is shared by all output neurons. And each kernel can be flattened as a column vector. And after that, this column vector can be mapped or can be translated to the conductance of a column of a Memristor array. Therefore, the input neurons, the convolution operation can be, the convolution operation are physically implemented by scanning an input image such as a handwritten digit um, by a convolution window, which provides the voltage bias, to the Memristor array, and the summed current constitutes output feature maps. These summed currents, as mentioned in the early slides, are physically worked out by Ohm's law and Kirchhoff's law. So as a result, no matter how large the size of the kernel is and how many kernels there are, each stride of the convolution is carried out by a single computational step. So based on that, we built a simple 4-layer convolutional neural network that is trained in real time to classify the MNIST handwritten digit, which is the first of its kind made by Memristors. The handwritten digits are first processed by two convolution layers that are physically implemented on Memristors, then downsized by a maximum pooling layer, followed by a dense output layer. Both convolution layers and the the fully connected layers are physically implemented on Memristor arrays. This network is in situ trained in a supervised manner, and the classification accuracy, you will find that out the classification accuracy rises very quickly. And in the meanwhile, you can see the conductance of the Memristors. They gradually converge, and after 2 epochs of training, the network correctly classifies around 93% of the handwritten digits of the test sets by just using 1,000 weights, and this accuracy is just 3% different from the software accuracy, indicating the robust learning of the Memristors. In addition to dense and convolution layers, recurrent layers are widely used for applications such as natural language processing. The simplest recurrent layer is a computational graph with looped connections. This can actually be implemented on 2 Memristor arrays with shared output lines. The input neurons or recurrent neurons provide the voltage to the Memristor arrays, and the output currents of 2 Memristor arrays they are automatically computed by Ohm's law and Kirchhoff's law. They will be converted back to voltages to bias the recurrent Memristor arrays in the next time step, therefore implementing the recurrent connections, recurrent topologies. In reality, such recurrent topologies can be much more complicated, such as introducing the long short-term memory function to better catch the long-term temporal correlations of the inputs. And in addition, another upgrade could be we can replace the inputs with we can replace ordinary input with convolutions to catch up the spatial correlation of the inputs. Therefore, a single layer like this will be concurrently identify the spatial and temporal features. So with that, we built a 3-layer recurrent convolutional neural network to classify small videos, the first of its kind made by Memristors. So at each time step, a frame of the video as well as the recurrent inputs are physically convolved by Memristor kernels, which implements the long short-term memory function. In the last time step, the output of the recurrent convolution layer is downsampled by a max pooling layer, followed by a dense output layer. Both the recurrent convolution layer as well as the dense output layer are physically implemented on the Memristor arrays. This neural network is in situ trained. The classification accuracy rises quickly, and after 2 epochs of training, the Memristors achieve software accuracy in classifying small videos, which again proves the robustness of Memristors in situ learning. So all these examples show both these 2 examples show the promise of Memristors for neuromorphic computing and machine learning, thanks to their ability to compute using novel physical processes or the novel mechanisms. And more excitingly, this technology is no longer something in lab now. There is an increasing number of players from the industry, including HP Enterprise, IBM, TSMC, Huawei, Panasonic, and Applied Materials. However, to push Memrister-based bio-inspired computing one step further, there's still plenty of work on devices, integration, favorite circuits, and applications. I will illustrate some of the examples. For example, in terms of device optimization, a fundamental limit of Memrister is that it's a resistor, so it constantly converts electricity to joule heating. And can we get rid of such joule heating? Yes, we probably can. We could convert a memristor into a mem capacitor with tunable capacitance. For example, we can add a series capacitance to a silver diffusion memristor. When the silver memristor is in its off state, essentially this is an open circuit, so there are 2 capacitors in series. And once the silver memristor is switched on, it will short this parallel capacitor. So this series capacitance will dominate. And such a device actually exhibits a charge versus voltage relation of hysteresis loops, which illustrates this is a tunable capacitor or mem capacitor. This volatile mem capacitor could also be used as the gate of a transistor, which behaves like a neuron. For example, the incoming spikes will be integrated, will switch on the mem capacitor periodically, leading to spikes or the current spikes from the source current spikes across the source and drain of the transistor that is beneath the silver memristor. And such devices could even be integrated to form a capacitive neural network that is able to have the potential to realize very energy efficient spiking neural networks. In terms of integration, 3D stacked memristors have been developed for storage class memory like Intel Optane. In addition, in our group, we have also demonstrated that 3D stacked memristors can be used for computing. They can naturally implement convolution operations if they are integrated using a special architecture. This 3D circuit topology will naturally benefit convolutional neural networks that is widely used for computer vision. In addition, Prof. Chai Yang's group from Polytech U has innovated one step further. They have proposed the so-called in-sensor computing, where it can bypass the current favorite circuit limitation, or the sensors are usually digitized first, and the digitized sensing information will be passed in a sequential manner to an external computer processor. And this bottleneck can also be solved with an innovation in integration, that is, the sensing and the processing units can be fused together or so-called in-sensing computing, which could be one step further to combine the sensing, processing, and the memory capabilities in one body. In addition, favorite circuits uh, like like the memory chips are usually mm, in terms of favorite circuits, actually the overall energy efficiency of a Memristor machine learning system is largely determined by the digital part and the analog digital conversions. For example, in our early systems, the chips are interfaced with 16-bit DACs and transimpedance amplifiers and ADCs that are physically integrated on these PCB boards that is developed by HP Lab. However, such PCB integration is very bulky and energy inefficient. So what what we did in the last year is like um, like my former team have established a computer. We collaborated with this company, TetraMem, that we have developed a, a 128 by 64 Memristor array with integrated uh, DSAs with integrated analog digital conversion circuits and the drive-in sensing circuits using TSMC 180 nanometer technology nodes. And this SEM shows the cutting profile of this chip. So these are the metal layers beneath. And the memristors are back-end integrated in our lab. And actually you can find this as a crossbar structure. So each memristor is at this, at a kind of this like in cross junction. And in addition, we have constructed an embedded system that is able to command the chip. That can be this consists of an ARM processor that runs Linux and Python and a customized machine learning framework. Um, and this ARM processor um, via a direct memory access controller communicates with a customized IP that has two extra modules. One is our RAM module, which controls the programming, reading, and computing of the memory array, and the neural network module that is responsible for the activation and the pooling functions of the neural networks. And in future, this uh, parts on FPGA will be combined with the memory array as well as its favorite driving circuits. And in terms of applications, memristos have already revealed the advantages for being the building blocks of both hardware spiking and artificial neural networks. And in addition, the energy efficient vector matrix multiplications make them capable to compress images by performing discrete cosine transformations, which is one of the pioneer work by Professor Ken Lee at Hong Kong U, as well as solving systems of linear equations using conjugated gradient method that is widely used for scientific computing. And all of these applications are just examples on how memristos may change our way of computing in the near future. And I would like to, in the last slide, I would like to show you some examples of what's available from the industry. So in 2008, Panasonic has unveiled 40 nanometer a computing in-memory chip made of memristors that builds on 40 nanometer technology nodes that has demonstrated 66.5 tera operations per second per watt. So in 2019, people from IBM Tokyo and IBM California have implemented this uh, computing in-memory chip to perform spiking neural networks or the that have dedicated that so that the synapses actually evolve with their own plasticity. So it's not a machine learning chip. It's a it's a chip like the Intel Loki or IBM True North. this chip, because it's not a machine learning chip, so this tera operations per, so it actually operates at 20 hertz, slightly faster than our brain, and each synaptic operation consists just of 5.39 picojoule. And in 2020, uh, people from Tsinghua University of Taiwan, the National Tsinghua University, they collaborated with TSMC. They have developed this 22 nanometer computing in memory chip made of memristors that consists of 2 million memristors that has demonstrated more than 100 tera operations per second per watt operation. So are the these are the real progress that shows the light of that shows the promise of memristors in terms of replacing in terms of being commercialization. So the memory-based computing will probably enter the will will be available to purchase and will be part of our like desktops in very short time. And what's next? And I guess probably like I guess the research teams in Hong Kong will make the next milestone at like in Hong Kong. And with all of this, I would like to thank my collaborators and former group members, Professor Joshua Ang, Professor Chen Weixia, and Dr. Ken Li, Dr. Peng Li from UMass, and people from Tetramem and HPE Lab. And that's all of my presentation. And thank you very much for your privilege of time.
Okay, thank you, Professor Wang, for the very wonderful talk and a very comprehensive introduction. Okay, it's very inspiring. So now it's Q&A time. You can raise your hand and I will ask you to speak up in sequence, or you can type your questions in the chat box and I can ask on behalf of you. So any questions? Okay, there's one question in the chat box. So when talking about integrated and fire phenomena, you built an electrical model for cell membrane using memristor and the capacitor. Could you please explain more on the detailed behavior of this model and how such a model imitates the integrate and fire phenomena? Okay, like this one, yeah.
Thanks for this question. Yeah, this is a very good question. The integrate and fire behavior actually refers to integrate and fire is a relatively simplified model of our neural cells. Um, uh, it's not as complicated as so-called HH model that provides a much more faithful and highly fidel description of our neurons. So what the integration and fire model says is that there is a state variable that for example, the charge here, when the incoming stimulation comes, they will charge up this capacitor. So once the voltage reaches a threshold voltage, because the memristor is usually in its off state. So at the beginning, you could assume this is an open circuit. But once the voltage once the charge accumulated at this capacitor reaches a threshold voltage, this memristor will be switched on as represented by its color. So if it's red, it will be very conductive. And these charges will be, these accumulated electrons will be discharged through this memristor. So after that, the memristor has, actually there will be no charge. And since the memristor will spontaneously relax back to its off state, so this will actually reinstate the system to the case that there is no charge at all, and the system will be able to accumulate the incoming spikes again. So it's actually like a counter of the incoming spikes. So once, say for example, once there are 5 incoming spikes, the memristor will be switched on once to indicate the neuron has received 5 incoming spikes. So this is actually what integration and file implies. And actually for leaky, this means for leaky, if there is an integrator that is leaky, that means the summed up or the number of, for example, it has, in case it have received a couple of spikes, but the number of spikes has not reached the required number to produce, but in case if the number of spikes is not sufficient to trigger active to trigger action potential, and in case if there is a pause or a gap between the subsequent pulses, the neuron will, or the accumulated income will gradually start to decay. This is actually due to the charge that will be gradually dissipated through the non-ideal because the memristor can't be of infinite resistance. So the charge accumulated will also gradually be dissipated through this memristor. So in case if there are if the incoming spikes are less frequent, I would say if the incoming spikes are less dense or frequent, we may need more spikes to trigger the same action potential. So that's my understanding of this integration and fire. Minor, does that clarify your question?
Okay. So any other questions? And ask a question.
Hello, Professor Wang. I enjoyed your seminar a lot. I have a question on the unsupervised network. I remember it is a 8x3 network, but I forget about the page number. That
yes. Are you referring to this one?
Yes. I am a little curious about how can we make sure that the training result is what we want, like the trend is going to the position that we want instead of going away from what we want.
Yeah, this is a very good question. But unfortunately, in unsupervised learning, I guess, let me repeat your question. I guess you are referring to how can we assign like the neuron 1 to, like, for example, input letters U and M, how to assign neuron 2 to let it respond to input letters such as S, and neuron 3 reacts to input patterns like letter A. Unfortunately, for unsupervised learning, we are not supposed to have a control of this, but usually which neuron is associated to which to which category of the input, or actually a category or class of input. This is largely determined by the, for example, the sequence that you applied, or the the sequence of your training samples, as well as the very beginning, the weight, the initialization of the weight, or the weight before the training. I believe both of these, the combination of the training sequence and the initial patterns can somehow affect like the association between neurons and the classes of inputs. So in case if you want to play some tricks there, you may like to initiate the weights of your neural network for a couple of times, and you probably will find, for example, next time the first neuron will respond to letter S or class S or class A rather than class U and M. So yeah, this is my understanding.
Oh, thank you.
You are welcome.
Okay, any other questions? So actually, Professor Wang, I have a question. So actually,
Yes.
in your like a future direction, you mentioned the resistance of the memristor. So in a typical like artificial neural network implementation, is 10 kilo ohm enough or not? I see that you mentioned that you want to make it 100 kilo ohm. So however, if we make it very large, the current will be small, then you need to consume more energy on the ADC. So what are the considerations, okay, if you want to optimize the resistance?
Yes, Professor Xiao's question is a very excellent question. In fact, I think in terms of perhaps let me switch to a different slide. Um, yeah. Usually, since we measure the performance of the system instead of measure the performance of the individual array, so our goal of system optimization is to minimize the total power of everything, of all of them combined. So one of the power consumption definitely comes from resistive element. They contribute because of the Joule heating. So they naturally consumes energy and converts that into heat. So this actually tells this is partially determined by the resistance range or the conductance of the memristors. On the other hand, uh, the sensing and uh, or the sensing and the driving circuitry, particularly the sensing circuitry or the circuitry that digitize, because usually the analog computing results will be digitized. For digitizing circuits, as Professor Xiao mentioned, there is also a concern, particularly in case if the resistance is too large. What will happen is this. First, there could be um, the RC delay could be relatively large because the time to settle down to, for example, like the voltage across a column, like the stabilization time of this will be much longer. So this will actually have negative impact to the throughput, to the computing throughput of the system. And in addition, as Professor mentioned, um, to sense such small current, uh, there could be some challenge, usually particularly in case if there are multiple ways to sense the current, such as using transimpedance amplifier to convert a current to voltage, or we could also use current comparators or current sensing amplifiers. Um, and this will make that more difficult, and a direct result could be this part of the fabric circuit will cause much larger chip area. That is usually what we don't want. So I would say this is a system optimization problem. We have some hyperparameters like the resistance of each memristor and the like the circuits available that or the hyperparameters of the sensing circuits, and we are usually trying to identify a combination that maximize our expectation. For example, we may, for certain applications, we may have a higher expectation of the throughput, but less strict requirement of its energy efficiency. So this optimization problem depends on the specific task that we hope to apply the system to. So this is my understanding.
Thank you, thank you. Okay, any other questions? Okay, okay, if not, I think that's all. Let's thank Professor Wang again for the wonderful seminar. Okay, thank you.
Thank you very much for this opportunity, and it's my very pleasure and honor to share my research, and hope to see you guys again.